Hello everyone. In today's video, I would like to do a quick overview of some of the essential ideas of Calculus 1, and as well as some of the essential formulas and techniques that were used in Calculus 1 to calculate derivatives and to use derivatives in physical applications. The reason that I want to go over this material with you again is because a lot of the techniques from Calculus 1, a lot of the ideas from Calculus 1, a lot of the applications from Calculus 1 are used again in Calculus 4 as we deal in Calc 4 with derivatives of multivariable functions as opposed to Calc 1 when we were dealing with derivatives of single variable functions. So let's begin by reminding ourselves what is the derivative of a function. The derivative of a function, let me call the function f of x, the derivative of the function was represented in symbols by f prime of x, f prime, where the prime is corresponding to this little dash next to the function name, f prime of x. And I'm going to write it out in symbols, what the definition is, and then we're going to interpret what these symbols are telling us about the situation. The derivative of the function f of x is found by taking a small change in the output values, delta y, dividing that by a small change in the input values, delta x, and then allowing that change in the input values, the delta x, to get smaller and smaller and smaller. So we're taking an extremely small change in outputs and dividing it by an extremely small change in inputs. And that ratio of output change to input change is the derivative of the function. So to write that out in words, the derivative is the ratio um, between a very small change in the input and the resulting small change in the output. Now, I've just written one symbolic notation for the derivative of a function f of x, which is the notation that has this little prime next to the function name. But in addition to that, you can see many other different notations used to represent the derivative of a function y equals f of x. You may also see it called dy dx, or you may also see it called df dx. These are also used to represent the derivative of the function y equals f of x. And I kind of like these notations in fraction format here because these notations are very closely related to what the derivative actually is. It's a very small change in the output value, represented here by a dy, divided by a very, very small change in the input value, represented by a dx. And so this dy represents a very small delta y. This dx represents a very small delta x. So this is extremely nice notation here with the fractions because it reminds you what a derivative actually is. It's this ratio between a small change in the output and the small change in the input. Now, the derivative tells you many different things about the original function. The first thing that the derivative tells you about the original function is how that function is changing, the rate at which that function is changing. And a quintessential example of the derivative as a rate of change is to say, okay, suppose I have y as a function of time, and the function is outputting the position of a moving object at that time. In this case, the derivative of this function with respect to time, which we could also write as dy over dt, would represent the rate at which the position of the object is changing over time, also known in physics as the object's velocity. And this makes sense because back in algebra, you may have learned about this equation used to relate distance, rate, and time, which is called the DIRT equation. Distance equals rate times time, known as DIRT for short. If I rewrite this equation, we can see that the rate is equal to the amount of distance traveled divided by the amount of time it takes to traverse that distance. And we can see that same division happening here in the notation for the derivative. The rate at which the object is moving is this ratio between the amount of distance that the object has traveled, represented by this small change in the object's position, and divided by the amount of time it took to traverse that distance, represented by this small difference in the initial time and the final time for the movement, dy over dt. Graphically, the derivative also tells you the approximate slope of the graph of f of x, or to be more precise, the slope of a tangent line to the graph of f of x. So, for example, if I had my x and y axes here, and the graph of my function f of x looked like this, if I chose a specific location along this graph, for example, maybe here, let me call that just generically x equals a, and if I calculated the value of the derivative at this specific location, this would tell me the slope of the line tangent to the graph at x equals a. If I draw that tangent line in this picture, it's going to be attached to the graph at x equals a. It's going to be attached to the graph, and it's going to align with the graph at that location. So in this particular drawn example, we can see that the tangent line that we have just drawn attached to the graph at this particular location would have a positive slope because the graph is moving up as we go from left to right. So this tangent line having a positive slope would be correlated to the derivative being positive at that point. Following this same reasoning, you can use the sign of the derivative to tell you about the behavior of the graph at various locations. For example, if I set up a little table here between f prime at a specific location A and the original function at a specific location A, I can say that if f prime of A is positive, as it is in this example at this location, If f prime of a is positive so that the tangent line is tilted upward, that is a sign that the function is increasing at that location and the function is getting larger as we move from left and right to right across the graph. If I drew my tangent line at a different location, such that the tangent line had a negative slope instead of a positive slope, for example, maybe somewhere back here. Here, the tangent line is tilted downward, so f prime of a would be negative to capture the fact that the line at this location would have a negative slope. And if the tangent line has a negative slope, that indicates that the graph is tilted downward at that location. So the graph is decreasing, the outputs are getting smaller as we move from left to right. Now it can also happen that when you graph your tangent line, the tangent line is perfectly horizontal to the graph at that location. For example, that might happen here at the top of this little hill. At this location, f prime of a is 0 because the tangent line that we have drawn is perfectly horizontal and flat. Then the original function f of a has somewhat flattened out at that location. So this usually corresponds to either the top of a hill or, for example, over here, the graph also flattens out a little bit at the bottom of this little pink valley. So if your derivative is exactly equal to 0 at a certain location, that indicates that the graph of the original function has somewhat flattened out. So now that we've understood conceptually what the derivative represents, let's talk about some of the things that the derivative is used to calculate in the real world. Derivatives are used to calculate velocities, accelerations, and inflection points. So for example, as we've already discussed up here, if you have a function in physics which is tracking the position of an object over time, then the derivative of that position function would tell you how fast the position is changing, which is known in physics as velocity. If you take another derivative, if you take what's called the second derivative, you can get the acceleration of the object, which tells you how fast the object's velocity is changing over time. Roughly speaking, how quickly is it speeding up or slowing down? You may also hear the word velocity used in business. For example, if you have a function c of t that represents your costs or spending as a function of time, then c prime of t would tell you how your costs are changing over time. If they're going up or down, and this is known sometimes in business as your spending velocity. You will also see derivatives used in business to find something which is called an inflection point. An inflection point, if you have a graph over time, for example, maybe this graph represents consumer interest in a topic over time. Then the inflection point is the moment where the trend begins to change. In this picture, the inflection point would be located right here, where the graph changes from what we call concave up, shaped like an upward facing bowl, to what we call concave down, which is shaped like a downward facing bowl. The inflection point in business is the moment when you start to get a sense consumer interest may soon begin to fall off, is probably going to start to drop in the near future. So in business, the inflection point is a very, very important moment because this is usually when businesses will start to change their practices and change what they are doing because they are anticipating a change in consumer behavior a little bit later in time. The third thing that derivatives are used to do are to do what are called optimizations. For example, if you are running a business, you may be interested in trying to maximize your business's profits. So suppose that I had a function P of X, which was capturing company profits as a function of the price X set for some service. If you're charging more money for your service, then each customer is paying you extra dollars. So in theory, that would increase your profits. However, if you set your price too high, fewer people will be able or will be interested in using your service. So what is the sort of sweet spot on the price that you can set for your service to get your profits as high as possible, to get lots of customers, each of whom is paying you a decent amount of money? In this situation, our goal is to make profit as large as possible. And if I graph the profit function, for example, if my profit function looks something like this, then I'm interested in the highest point on this graph right here. This would be the location where the outputs, the profits, are as high as possible. If I look at this point on the graph, I can see that the tangent line at that highest point is horizontal. So the highest point on the graph has this characteristic that at this location, the derivative of the profit function is equal to 0. Derivatives are also really nice for predicting future values of a particular quantity. So, for example, suppose that I am an administrator at Green River College, and I know one, the number of GRC students in 2025, and two, the rate of change of GRC students in 2025. And I want to make a prediction about how many Green River College students might be around in 2026. Because if I am going to have a lot of extra students in the future, then I'm going to have to make sure to hire enough teachers and enough staff to serve all those students so that they have enough classes to take to complete their degrees on time. Now remember that the derivative of a function is very closely related to a small change in output functions divided by a small change in the input of the function. So if I want to get a sense of how the output of a function will change, I can get an approximate prediction of that change by taking the derivative of the function, the rate of change of the function, and multiplying it by the change in inputs. Now, in this context, the rate of change of the function would be what I have captured in my data right here in number 2. And the change in the inputs would be the change in the year. So in this case, it would be the change in the year 2026, the future year, as compared to the current year, 2025. And I could use that to predict the effect on the number of students enrolled at Green River College. The delta Y in this context would be the students in 2026, which is what I'm trying to figure out, and the difference between that and the students at Green River College in 2025. So in this situation, I have information about F prime. I know the 2 years I'm looking at. I know the students that I have on the college campus this year. And so I could use all of that information in this equation to predict how many students will be on campus 1 year in the future. It's not going to be a perfect prediction. This is just an approximation after all, but it's a nice way to sort of get a read on what you might expect for the next year to help you to do planning, hire people, etc. in your business. Finally, let's talk about a little bit of how we actually calculate the derivative of a function. Now, when we're calculating derivatives, we start with derivative formulas for what are called the basic toolkit functions. And these are the basic functions from which all other functions are built. And these are the functions that you've learned about throughout your math career. Things like the power function, x to the n, things like the exponential function, things like the logarithm, things like sine and cosine. Every single other function really can be created by combining these functions in various ways. For example, the tangent function, the function tangent, can be found by dividing sine by cosine. We have derivative formulas for each of these basic toolkit functions. For example, if you have the function x to the power n, where n is whatever real number, the derivative of that function would be found by taking the exponent n, dropping it to the front, and then decreasing that exponent by 1. The derivative of the exponential is just the same exponential. The derivative of the natural log is the function 1 over x. The derivative of sine is cosine of x. And the derivative of cosine is negative sine of x. And you really should have all 5 of these formulas memorized. These are the absolute most basic derivative formulas, and you should have all 5 of them memorized for sure. Now, this power rule here is actually more useful than it seems at first because there are many other kinds of expressions that can be rewritten to have this format x to the power n. For example, reciprocals like 1 over x squared can be rewritten in this format because reciprocals correspond to negative exponents. So if I wanted to find the derivative of the function 1 over x squared, I could instead find the derivative of x to the power minus 2. And I could accomplish that using power rule by dropping that power to the front and then decreasing it by 1 unit. Likewise, roots, like the cube root of x, can be expressed in an exponential format. Roots correspond to exponents which are fractions. So if I was asked to find the derivative of something like a cube root of x, I can use power rule to calculate that and find the derivative of x to the power 1/3. And using power rule, I could just drop that exponent to the front and then decrease that exponent by 1 unit. Now, earlier we said that most functions can be created by combining these 5 toolkit functions in various ways. And there are derivative rules that allow us to find derivatives of combinations of the toolkit functions, different rules depending on precisely how the functions have been combined. For example, if you are dealing with a combination of toolkit functions that has been accomplished by way of addition, for example, if you are trying to find the derivative of the sum of a function called f of x and a function called g of x, then that can be accomplished just by finding the derivative of each function separately and then adding those results together. And this is called the sum rule because it deals with how to take derivatives of sums. Similarly, if you're dealing with a combination of toolkit functions that has been achieved via subtraction, via a difference, then you can use the difference rule to find the derivative of that particular combination. And the difference rule says, again, you can just find the derivative of each piece of the difference separately. If you have a number, for example, a number c, multiplied by one of the toolkit functions, then you can essentially just set that number aside, copy it down, and take the derivative of just the function portion of that product, and this is called the constant multiple rule. Now, unfortunately, the remaining derivative rules are a little bit more complicated. If you are trying to find the derivative of a combination of two functions that has been achieved by way of multiplication, a product of two functions, the rule for this is take the derivative of the first function, multiply it by the second, and then take the derivative of the second function and multiply it by the first. Likewise, if you have two functions which have been combined via division, there's a relatively complicated rule for that. We take the bottom function, multiply it by the derivative of the top function, subtract the top function times the derivative of the bottom function, and put that all over the bottom function squared. This is the so-called quotient rule, because it is helping you to find derivatives of quotients. And finally, the last main derivative rule that is used for finding derivatives of combinations of functions is what's called the chain rule, where the functions have been combined using composition, where we take the derivative of the outer function, leaving the inner function alone, and then multiply that by the derivative of the inner function. This is chain rule. So to give you an example of using some combination of these rules in tandem with these basic derivative formulas for the 5 toolkit functions. For example, if somebody says to me, find the derivative, find dy dx for the function, let's say y is equal to 2e to the x minus 4 cosine of x. In this case, I have a difference of constant multiples of the toolkit function e to the x and the toolkit function cosine. So I have built this function by combining e to the x and cosine in this way. So I will find the derivative using the formulas for e to the x and cosine x, and also using the constant multiple rule and the difference rule. So if you see how quickly I just calculated that derivative, that is approximately how quickly you should be able to calculate derivatives that are as simple as this one. You should not be looking up these formulas in a textbook. You should not have to Google these formulas. You should not have to Google these rules. This is something that you should just be able to do, like tying your shoes or turning on your car. Just a regular course of mathematical life that you should not have to look up as you are doing it. For a slightly more complicated example, suppose I said find dy dx for y equals x e to the 2x. So I have a few things going on here. I have a product of x multiplied by this exponential, and then within that exponential is a composition where the x has been replaced by the function 2 times x, and there's a constant multiple happening up there. So to tackle this situation, not only would I be using power rule and the formula for the derivative of e to the x, I would also be using product rule, I would also be using chain rule, and I would also be using constant multiple rule to find the derivative of this particular combination of toolkit functions. So starting with product rule, I have the first function times the derivative of the second function, and then the second function times the derivative of the first. The derivative of e to the x can be found using chain rule, which says take the derivative of the exponential, which leaves it unchanged, and then multiply by the derivative of the inner function, 2x. Likewise, here in the back, the derivative of x is just 1. And then finishing this final derivative of 2x, the result of that is just 2. So I get 2x e to the 2x, and then plus the term e to the 2x. And this would be the derivative. Once again, as quickly as I just calculated this derivative, that's the level of speed and efficiency that you are aiming for in your work as well. Because these are really basic derivatives. So this is like tying your shoes, this is like turning on your car. This is not stuff that you really should have to look up. This is stuff that you should just know because you've done it so many times. So that concludes our review of Calculus 1, reviewing what the derivative is conceptually, how it is written in symbolic notation, some of its physical real-world applications, and some of the ways that the derivative is calculated.